Day 8, 3, 2, 1. The expedition comes across a peculiar patch of tall trees all planted carefully in a grid. The elves explain that a previous expedition planted these trees as a reforestation effort. Now they're curious if this would be a good location for a treehouse. First, determine whether there is enough tree cover here to keep a treehouse hidden. To do this, you need to count the number of trees that are visible from outside the grid when looking directly along a row or column. The elves have already launched a quadcopter to generate a map with the height of each tree, your puzzle input. This is very photosynthesis-like. For example, grid. Each tree is represented as a single digit whose value is its height, where 0 is the shortest and 9 is the tallest. A tree is visible if all the other trees between it and an edge of the grid are shorter than it. Only consider trees in the same row or column. That is, you only look up, down, left, right from any given tree. All the trees around the edge of the grid are visible since they are already on the edge. There are no trees to block the view. In this example, that only leaves the interior 9 trees to consider. The top left 5 is visible. I'm guessing because it's 0 and 2. Watch on top. It is invisible from the right or bottom. The top middle 5 is visible from the right, top and right. So the tree is visible if all other trees between it and an edge of the grid are shorter than it. So if it's top, that includes, oh, top middle. Haha, okay, that's my bad. All right, the top right one is not visible from any direction. For it to be visible, there would need to only be trees of height 0 between it and an edge. The left middle 5 is visible, but only from the right. Okay. The right, okay. With 16 trees visible on the edge, another 5 visible on the interior, a total of 21 trees are visible in this arrangement. Consider a map. How many trees are visible from outside the grid? Okay. This one should be fairly straightforward. We can do it in a pretty naive way that's still going to be fast enough. Okay. Let's grab the test input, and then let's also grab our puzzle input. Yeah, so that should be easy enough to do naively. That's a pretty small amount of data. Okay. Okay, to save time again, I'm just going to walk through the solution instead of having you watch me build it out for the first part. So basically, I just did a mutable list of ints for the tree. You could use an array or something as well. We already know the sizes for both dimensions, so that should be easy enough. That's just what I did on the fly. Either one for this size of input does not matter. And then of course the total visible, which we'll return later. For every line in the input, and a line is going to basically be a row of trees, right? We're going to add a new list item to our tree grove. That's basically just going to be the next line down. And then for every item in that line, every character, we're going to convert it to an integer and then save it easy enough. And so that's going to basically build this input array into memory. Easy enough. And then to test each tree, for every row in the trees, and then for every column in that row, we're going to just basically test that individual tree. So visible is false by default. If it's, or we grab its height, it's just index trees RC. To the left is easiest because we've already been iterating through the left. I certainly could have done the same exact thing I did below it, but it's easy enough to just keep track as you're going along. And so if it's the tallest in the row, update the tallest in the row, and then set it to true. If it's not the tallest in the row, we don't bother with the left side. To test the right, we're going to take the sublist of this index plus 1 all the way to the end of that row. And then we're just going to take the max of those. So that way we know the highest tree to our right. If it's null, that just means there's nothing to our right, so we're on the right side. in which case we need the shade to be below 0 so we can test positive for it. And basically, if we're taller than the highest tree to our right, we're visible. And then the same thing for above and below, but instead of doing a sublist, we need to basically map. And map index will let you do kind of a cute thing where it gives you both the index and the actual value. So this is going to give us the I, which is the index or the row number, and then row, which is actually going to be the tree row output. If the index is less than our current row, so if it's above us, then we're going to return that height. If it's not, meaning it's our row or lower, then we're going to return -1. And then we want the max of that or null. Again, if it's null, then that just means there's nothing above us and should be visible. Same thing for below, but instead of testing it I less than our current row, we're going to test it I greater than our current row, so it's going to get all the rows below us. If the visible flag has been set, we're going to increment, and at the end of all of this looping, then we're going to just return the total visible numbers. All right, 1763. We will try that. $17.63. That's the right answer. You are 1 gold star close. Okay, part 2. Content with the amount of tree cover available, the elves just need to know the best spot to build their treehouse. They would like to be able to see a lot of trees. To measure the viewing distance from a given tree, look up, down, left, and right from that tree. Stop if you reach an edge or at the first tree that is the same height or taller than the tree under consideration. If a tree is right on the edge, at least one of its viewing distances will be 0. The elves don't care about distant trees taller than those found by the rules above. The proposed treehouse has large eaves to keep it dry, so they won't be able to see higher than the treehouse anyway. Okay. In the above example, consider the middle 5 in the second row. Looking up, its view is not blocked, so it can see 1 tree. Looking left, its view is blocked immediately. It can see only 1 tree. Looking to the right, its view is not blocked. It can see 2 trees. And looking down, its view is blocked eventually. You can see the 3 and the 5. A tree's scenic score is found this way, by multiplying together its viewing distance in each of the 4 directions. For this tree, this is 4, found by multiplying 1, 1, 2, 2. Okay. However, you can do even better. Consider the tree of height 5 in the middle of the 4th row, blah, blah, blah. That scenic score is 8. This is the ideal spot for the treehouse. Consider each tree on your map. What is the highest scenic score possible for any tree? So this is fairly similar, but also fairly different because it's going to be basically backwards for almost all these things. All right, so the problem is we won't be able to do the cute little maps thing because we don't care about if it's blocked, we care about when it's blocked. So we actually kind of need to iterate through each of them. I'm sure there's probably a good way to do that with folding, but we can just do it the naive way. It's fine. Again, this is not very much input, so. All right, so what we want to do is we have our tree grid like we did before, and then same thing, we're going to say for row in trees dot indices, and then for column in trees are, if I can find the right button, dot indices. This time we'll probably just have to do 4 for loops. I mean, again, I'm sure there's an easier way to make that a little cleaner, but as far as logic-wise, it's just going to be the easiest. For x in c down to 0. So down to is basically the exact opposite of until. And so instead of counting up, we're just counting down by 1 each time. Easy enough. So for x down and c down to 0, and we actually want c minus down 1 down to 0. If trees are x is it's less than height, we want this to increment, else we want to break. Left plus plus break, and if there aren't any, it'll just fall out. Okay. And then basically we need to just repeat this a few times. And then xc down and down. And then this should be the for loop for the inside. So val scenic is going to be left times right times up times down. If scenic, or actually we can just make this easier, we'll say best view is equal to max of best view and scenic. And then return best view. Okay. Exception check failed. Is my height not correct? My height is not correct. That was the only problem. Okay. And let's scroll down, throw that answer in, submit. Woohoo! We are 1 star closer. You completed day 8. Okay, guys. That is it for today. I'll see you tomorrow.